connecting your world.
We interact with software as if it's weightless. We drag and drop files, stream video, and send emails, experiencing a clean, abstract digital space. But beneath that glass screen, the internet runs on raw, heavy hardware. Every piece of media you consume is, at its core, just abstract mathematics. It's an arrangement of discrete ones and zeros, trapped in the logical memory banks of a machine. But math itself doesn't have physical form. A mathematical concept cannot travel through a solid copper wire or fly through open air to reach a smartphone. To actually move information across the real world, those abstract binary digits have to be transformed into physical energy. In the architecture of computer networking, this vital job falls to the base of the system, Layer 1, also known as the physical layer. Of all the complex systems that make the internet work, this is the only part that actually deals with tangible reality, specifying the cables, connectors, and electrical signals required to move data. Without this crucial translation step into the physical realm, the entire digital world would be completely paralyzed, locked away inside millions of isolated machines. If you look inside a computer, right at the point where the network cable plugs in, you'll find the border crossing. This is handled by a specialized integrated circuit known as the PHY, or physical layer transceiver. It acts as the literal gateway between the logical digital domain and the physical analog world. The PHY chip's main job is called line coding. You can think of line coding as a strict rulebook for mapping digital ones and zeros onto tangible physical voltages that can travel down a wire. This chart shows a basic line coding method known as NRZL, or non-return to zero level. The rules are straightforward. The hardware represents 0 by holding a positive voltage plateau and represents a 1 by dropping to a negative voltage plateau. But this simple system has a critical design flaw. If a computer sends a long, uninterrupted sequence of zeros, the voltage never changes state. It stays perfectly flat. Without any shifts in voltage, the receiving computer eventually loses its internal sense of time. It becomes impossible to tell exactly where one bit ends and the next one begins. Direct voltage mapping turns out to be too fragile for reliable networking. Engineers had to develop smarter signaling techniques to keep the transmitting and receiving devices perfectly synced. The solution was to design advanced line codes that secretly embed a ticking clock directly into the data stream itself. This diagram illustrates Manchester encoding. Here, the hardware forces a voltage transition in the exact middle of every single bit, regardless of whether the data is a 1 or a 0. That constant midpoint shift acts like a built-in metronome, guaranteeing synchronization. This chart shows bipolar AMI encoding. Instead of 2 voltage levels, it uses 3, positive, 0, and negative. 0 bits map to a neutral voltage, but it alternates the polarity of the 1 bits, balancing the electrical charge to keep the hardware stable. Copper wires and voltage pulses are highly effective for short distances, but modern data centers require speeds that push past the limits of electricity, so they abandon electricity for photons. Transceivers use tiny lasers to fire perfectly timed pulses of light down glass fibers, down to the nanosecond. Whether utilizing copper voltage tricks or rapid bursts of laser light, the hardware relies on strict mathematical patterns to ensure the signal survives the chaotic journey through a physical medium. When you click a link to load a web page or hit play on a streaming movie, you don't see any of this happening. But beneath your screen, these exact line coding translations and laser modulations are being executed flawlessly, billions of times per second, across the globe. The PHY hardware absorbs the messy physics of the real world, the signal degradation, the heat, the background noise. Because the physical layer handles that friction, your operating system and web browsers never have to account for the laws of physics. They just send their abstract math and trust the hardware to deliver it. The weightless, virtual spaces we experience every day only exist because a global network of physical hardware is constantly, silently translating abstract data.